All right, you got me again. So today now we'll talk about some more collaborative work now between me and Hector Perez. That's now at Relational AI. Before that, we were both at Carnegie Mellon, so that's kind of how we got started on this. And we'll be talking about the package DisjunctiveProgramming.jl. Just to acknowledge, though, so at our time at Carnegie Mellon, we were supervised and supported financially by Caro and Ignacio, so grateful for that, and Hector. This is his package. We'll just talk about, I just helped him kind of redo all of it. So we're going to talk about that today. So let's jump right into it. First off, what is generalized disjunctive programming? So this is perhaps better known in the chemi community. So there's disjunctive programming, but the generalized part of it seeks to generalize it a little bit beyond the typical context it's used in. Primarily with the use of nonlinear constraints, because in chemical engineering, nonlinearity is not something we can do away with. So basically, the key idea, though, is that we're going to conditionally enforce constraints based on Boolean variables. Here I'll call them G, which can be equal to true or false. Okay? And this will be in a collection of disjuncts, where typically only one of them in the collection is enforced. So you have, like, maybe we could do this or this, and depending on which one you choose constraints accordingly. So this comes up, for example, in expansion planning. I could build this one mega power plant or kind of these other smaller ones. Depending on which one I choose, I'll get the associated constraints with either one, is an example where this comes up. So this typically has as well the use of logic constraints, where we can take those Boolean variables and have kind of arbitrary logical constraints that you can make, denoted by that function omega, where you can have various logical operators like and, or, negation, implies, if and only if, etc. You can also have some constraint programming-like syntax, like these cardinality type constraint objects. And then there's systematic ways of converting these into algebraic constraints using something called conjunctive normal form that I won't go into detail today, but happy to talk about it afterward if anyone wants to know more about it. Okay, so this is just an old slide I stole from Hector. This is just showing, again, where chemi's kind of a technology selection problem where we have actually nested disjunctions. That's kind of Hector's thing. Won't go into too many details on that, but this is kind of higher than the old syntax. So here we get in some data. Then he declared his JuMP model with some variables and just variables for now. And he added in some global constraints. So these have nothing to do with disjunctive programming, just constraints to our problem. Then we get into this kind of what was the disjunction macro. And you kind of have these constraints inside of it, and you can specify the reformulation and some naming conventions with nested disjunctions in there. And then we can keep going to define the rest of this problem. So we define the other disjunction in actually a slightly different syntax. And then we can add more constraints to the other one as well. And then we can do some other things to add in some stuff we want for the disjunctions. It has a lot of cool functionality, but not necessarily the most intuitive or compact syntax. So this was where it used to be. There's some more stuff there with the logic constraints. So some of the limitations, not necessarily the most intuitive syntax that kind of closely matches the math. We didn't have the ability to transform the model, we'll talk about that in a bit, and then change the transformation and resolve it. It also didn't really scale that well. If you had more than a handful of disjunctions, the build time would quickly get out of control. It also wasn't compatible with InfiniteOpt, which is kind of my thing. And it didn't support nonlinear expressions. So a number of limitations. So I went to Carnegie Mellon. I mentioned, hey, I'm kind of a JuMP guy. I like JuMP. And so I could probably help you, fix all these problems. So we went through and after about a year or so, changed pretty much everything and fixed those problems. So we'll talk about the new API now. So we have what we call logical variables. These are those Boolean type variables, which are defined on sets true or false. So they're not binary variables, not from 0 to 1. We purposely make this distinction. These are then used as what we call indicator variables to indicate if a particular disjunct is on or off. And these are also used to build those logical constraints. So to define these, you just load in disjunctive programming. We make a GDP model, and you can put in whatever solver you want. It's just a JuMP model that has some extra stuff added onto it. Then you just define your variable the usual way. The only thing you do differently is you add on this logical tag. Otherwise, the syntax is the same as JuMP. To actually make a disjunction then, so disjuncts are identified using a logical variable, the indicator. So here we just make our model, and we have these logical variables there, the tag. Then we can make our constraints that we'd like to add to a particular disjunct. And so you just make your constraint. We have a disjunct, and we say, hey, we want to have the disjunct associated with this particular logical variable, y. And so these are being all the constraints I add to disjunct 1. These are going to be all the constraints I add to disjunct 2. And actually, I'm going to make 10 different disjunctions. So we're actually making 10 of disjunct 1 and 10 of disjunct 2. And then, covered by this plant a little bit, we then can make the disjunction, which is just a disjunction macro, where you just give it basically the vector of indicators that define your disjuncts. The reason why it's a macro is so you could do multiple disjunctions at once. In this case, we're making 10 disjunctions indexed by j, where each particular one is going to take a slice of y, basically y1, y2, for that particular index j. So this is making 10 disjunctions. Each disjunction has 2 disjuncts. To make logical constraints, we support the following operators, so and, or, negation, implies, if and only if. We use JuMP's Boolean syntax, so here you can use whatever logic you want with the logical variables, and then you just have this equals true at the end to kind of signify it's a logical constraint. We also support cardinality constraints. So we added in at most at least exactly. There's some similar things in JuMP, but because we can use some special properties of these being logical variables, this ends up being much more efficient in terms of solving the problem of these particular sets. And so we just use the classic function and set syntax to define these. So that gives us a way to define our problem. To actually solve it now, this is just showing some different techniques and the relaxations you get. We think of reformulations for the disjunctions. So the key idea is you can take those disjunctions with the logical variables, convert the logical variables into binary variables, and then do some sort of reformulation to typically get a MIP. And so these reformulations are just done on the JuMP model directly, but they can also be undone. So you could like transform your model one way, solve it, transform it another way, solve the same model, and kind of have this mutability to efficiently try out different things. So we currently support big M, convex, well, whole method, or convex in some cases, and indicator constraints. So all you have to do is you just, when you optimize it, you specify this GDP keyword and put the method you want to use. Some of them have some options you can specify here. I just have the defaults being used. With big M, for instance, we actually find the tightest big M that we can get with some interval algebra. But you can also manually specify an M value if you prefer. We also have an extension API, so it's quite easy to add another method, and we plan to add some more. So with the logical constraints, what we do is we will automatically reformulate those into, if we need to, mixed integer linear constraints, or just linear constraints. We do this by converting to the conjunctive normal form behind the scenes, and then we can follow a recipe basically to turn the crank and get these out of it. Currently, that is all it does. It doesn't, it doesn't support other stuff at the moment. In the future, there's demand for it. We could generalize it so you could have some sort of API there to extend. So some plans for the future. We're currently working on making an MOI backend, so we could have the ability to have like some sort of meta solver to do some more advanced algorithms to solve this, not just a reformulation, such as the logical outer approximation. This is similar to what pyomod.gdp does. So working on that, just finding the right abstraction for this to work in MOI. It kind of breaks some assumptions there. We're also looking into adding more reformulation techniques, so like multiple big M, p-split. Again, pyomod.gdp has some inspiration for us to draw from there. Finally, the last thing I want to mention is we got this working for infinite dimensional GDPs, which is the only place this exists to my knowledge. So the basic idea here is we have disjunctions, but this time they can be infinite dimensional. So you could have space, time, uncertainty, all the usual InfiniteOpt type suspects. This comes up in quite a few different applications, such as control, expansion planning, strategic planning, scheduling. Anytime where you're going to have time or space or uncertainty coming into your problem, and you might want to turn and off constraints depending on some logical condition, this comes up. So for instance, with chance constraints, we can use this. So a chance constraint, typically, we could reformulate the probability in terms of expectation of an indicator, like so. You can actually represent that then in terms of, if you're doing a scenario-based approach, in terms of like disjunctions of over those, actually it doesn't have to be scenario-based, over those uncertainty parameters. So basically here the disjunction is if you satisfy that constraint or not, that's it. And then you repeat that over your uncertainty. And then we can aggregate that all together with some logic, saying basically if some aggregation logic is used, typically just the AND operator, then we can enforce the expectation of whether or not constraint is used or not. So what's actually cool is beyond just chance constraints, we can actually use arbitrary logic to put it together, not just like AND logic. You could use like union logic or something more complex to get a more generalized thing that might not be as conservative as just a joint chance constraint. Okay. And then the way to think about this is if we had equal probability in our PDF, is basically what we're doing is we're just considering like the fraction of satisfying our constraint being an acceptable amount. So if it was like 0.95, for 0.95% of the scenarios, we satisfy this constraint or not. But we can put this in InfiniteOpt. This is a little code snippet here where all you do is we now have an infinite GDP model. And we get these infinite logical variables now, because your logical variables can depend on time, space, uncertainty. And then you can just do everything normally. And then when we optimize, we can now specify a GDP method. What's cool about this is it's more efficient now to apply the transformations in InfiniteOpt, because you might only have a few constraints before you discretize, so it's much more efficient. And it also opens up the window to maybe do some InfiniteOpt specific type transformations on these GDP problems as well. So this is kind of a new thing, and we're kind of playing with it, and it's been good. So if you want to try it out, there's our QR code, and with that, I'm happy to take any questions. Thank you.